Greetings, it's Paul Bamberg. I still haven't quite recovered from a bad cold, but I'm going to do my best to narrate this R script that shows how to implement a binomial model for evolution of share prices. So, we're going to adopt the notion that the price change from one step to another is proportional to the price. That is, rather than saying a stock may go up or down by $2 no matter what, we'll say instead it may go up by 2% no matter what. And to start out, I'm going to do a 6-step process where at each step either the price gets multiplied by 1.18 or multiplied by 0.82. That is, it either goes up 18% or down 18%. You know the formula for calculating the probability of a price rise, and if you look down at the bottom of the screen, you'll see that came out to 0.5 because the expected change is 0. So, if the price on day 0 is 50, then I can calculate the price on day 1 by using the R function sample. Here what happens is I make U and D into a 2-component vector, and sample chooses with equal probability either the first component or the second component. So when I run this line, I will either get 59 or 41. I don't know which. If I run the line multiple times, sometimes I'll get 59, sometimes I'll get 41. Okay, now we can repeat this and generate a sequence of prices. So I'm going to create a 1-component vector named x that includes the price on day 0, and then I'm going to grow this vector to include the prices on later days. And I'm going to store those prices in a vector of numbers named prices. So what do I do on each day? I store the price that I most recently calculated and then multiply it either by 1.18 or 0.82. I have to remember to store the final price, and then I can display this. In R, everything is a vector. This is a vector with 7 components, prices on day 1 up through day 6. The stock seemed to be having a very bad time. It went down every single day, but if I ran it again, I'd get quite different results. And I can make a little plot of this. Well, since we're on a computer, we can have many more steps, and what I'm going to do is kind of interesting. I'm going to make the price changes smaller by a factor of 6, up or down 3% now, but I will use 6 squared times more steps for a total of 216 steps. Again, the probability of an up or down step is 50%. We'll change that later. And I run exactly the same code. And in this case, since there are 217 components in this vector, I'm not going to print it out. I'm just going to make a plot. And it looks like one of those stock charts you see from people who are trying to sell you technical analysis stuff over the web. As I said, if I do this different times, I can get different results. And here I've run through a bunch of colors and got 7 different examples of how the stock price might evolve in accordance with this model. Well, 7 times, 1,000 times, we don't have 1,000 different colors, but if I want to do 1,000 repetitions, I can store the result of those 1,000 repetitions in a 1,000 component numeric vector named final price, and I just run exactly the same code again. Now I've got an array of 1,000 final prices, and if I ask R to display a histogram, it becomes quite clear this is not well approximated by a normal distribution. There's a long tail to the right, and the reason is if a stock starts at a price of 50, it can never go below 0, but it can go up into the hundreds. However, if I compute the mean of these final prices, notice all these handy-dandy R functions for working on vectors as single entities. The value I get is very close to 50. That means that, as we expected, the share price is a martingale. Alternatively, I can look at the logarithm of the factor by which the price changed. I take final price divided by the initial price x0, form its logarithm, and freq equals false displays something that looks like a probability density rather than the actual number of occurrences. And then this one looks closer to normally distributed. I can compute on theoretical grounds the variance for a single step and then multiply by the number of steps, except put a lowercase v in here so that R is happy with this. And so now I can plot the distribution if I assume a normal distribution with a mean equal to 0 and a standard deviation equal to the square root of that estimated variance. And it matches up pretty well. There's only one thing wrong. The data seem shifted to the left relative to the normal distribution density function. And here's why. If I take the product of u and d, this is what would happen if we go up one day, down the next. The result is a little bit less than 1, and over time this accumulates to drive the mean stock price down. In fact, I can take the number of shares times the log of the expected change in 2 steps over 2, and I get a prediction that agrees very accurately with the actual decrease that we observed. Now, there's no need to do this step by step because R supports the binomial distribution along with all other standard distributions. So R binom will generate random numbers. In this case, I just want one of them from a binomial distribution where you make n trials with a probability p of an upward step. So this will generate a random number of upward steps. And then all I have to do is take the initial price, multiply n up times by the factor u, multiply capital N minus n up times by the factor d, and I have got the effect of capital N repetitions. And now there's no problem with doing 10,000 of them. Set up a vector to hold 10,000 final prices. Do exactly the same calculation more quickly using the binomial distribution. And again, you see that tail to the right. You see we still have a martingale, and that we understand why the logarithm, though normally distributed, has a slightly negative expectation. Now I'm going to change the model very slightly. In order to make the exponent be a random walk, instead of saying up by 18% or down by 18%, I'm going to say multiply by 1.18 or divide by 1.18. In the models you've been seeing in class, this is the situation where we either multiply or divide by the quantity I've been calling capital V. And because it's conventional, I'm going to take the logarithm of the up multiplier and call it sigma. Then for the downward step, I have the expectation of negative sigma. Everything else is just the same as before, so I'll run through this very quickly. Again, the histogram of final prices has a long tail to the right, but this time the mean final price is not 50, it's 54. What's gone wrong? What's gone wrong is we wrecked the martingale property for the prices, because now the expectation of the change in one day is slightly positive. You earn more money when you go up by 10% than you lose when the shares go down by the same, when you divide by 1.1. However, we fix something else. If we look at the histogram of logarithms, now it does appear nicely centered on 0, and indeed the mean of the logarithm is very, very close to 0. On theoretical grounds, I can calculate what the variance of the logarithm should be, and then I can confirm that result by displaying the density function for a normal distribution with a mean of 0 and the calculated standard deviation, and it all fits very well. Now I'm going to change the model very slightly again. I'm still using u equals 1.03. That is, an upward step multiplies the price by 1.03. A downward step divides by the same amount. And with a probability of 1/2, as we already know, the expectation was slightly positive. We can fix that by building in a little bit of price drift, and as you have calculated, the exponent for the drift is minus sigma squared over 2. If I take the exponential of that, I get a number that is very close to 1, but it's just enough smaller than 1 to fix the problem we have. So I'm now going to repeat 10,000 times with one tiny change. For each stage in the evolution, I multiply by drift. So I multiply the whole thing by drift to the capital N. Now when I look at the final prices, I still see that tail to the right, but I have restored the martingale property. The mean price is very close to 50. It's not changing with time. However, I've now messed up the martingale property for the logarithm. You can see that the mean of the logarithm is about minus 0.1. That's significantly less than 0. But I know exactly why that happened, because I built in the drift. If I just subtract n times mu from the logarithms, then I end up with something whose mean is precisely 0. That's like Deneen's saying w sub t tilde is equal to w sub t minus ct. So I've now succeeded in restoring both martingale properties. The prices are a martingale, and thanks to my little fudge with the drift, the exponent is also a martingale. In fact, I can choose any value I want for the drift, and if you choose to play with this script yourself, you can change this number. I really should write assignment operator. If you use an equal sign in R, it almost always works, but every once in a while something goes wrong, so you should always use this left arrow. Okay, now in this case, because the price is evolving, the random part is going to need to tend to drop it to offset the drift. And the way we're going to do that is by having the probability of an upstep be a little bit less than 1. I just typed in Deneen's formula for this on the next line, and I get about a 48.4% probability for an upstep. I can also compute this exactly from the drift, and I get almost precisely the same number. So we'll do this again 10,000 times. And look at the resulting histogram, the usual tail to the right. The martingale property is satisfied because we adjusted the probabilities in order to compensate for the drift, but we made an unsymmetric random walk now. It's true, the exponent goes up or down by the same amount, but the probability of an upstep is no longer 50%, and we can fix that. Deneen uses an approximate value that he calls gamma. The exact value is 2 times the probability of an upstep minus 1. And now when I look at the logarithms, they're approximately normally distributed. And after I correct for the fact that the probability for an upstep is different from 50%, I can get a mean of 0 for the logarithm. Finally, you can have arbitrary probability for an upstep and still, by introducing an appropriate drift, get both the price and the exponent to be martingales. So I'll still use u equals 1.03. For a downstep, I divide by 1.03. But now I'm going to say I want the upstep to happen with probability 3/4. In that case, I need a drift that will keep the price down. And it's easy to figure out the formula for that. Take its logarithm and get mu. And let's see what happens in this case. Initialize the price on day 0, set up an array to hold the prices, and what I'm doing now is to say every day while I use an upstep or downstep with the probability chosen from a vector whose 2 components are 75% and 25%, I also multiply by the drift that compensates for the asymmetry in that. And I will do exactly the same thing and see what the price evolution looks like. And you might have thought, because the probability of an upstep was now much larger than a downstep, things were going to look significantly different, but in fact it looks much the same. I can do this in different colors and the chart looks much the same as before. I can do this 10,000 times to see what the histogram looks like. Looks much like our other histograms. We've still got a martingale because we introduced a drift that compensated for the effect of the higher probability of an upstep. The exponent is not a martingale because although I've got a random walk with steps of equal size up and down, the probability is higher for the upstep. And either by using Deneen's gamma or the exact value 2p minus 1, I can correct for that and display a histogram of corrected logarithms that matches up beautifully with the normal distribution. I encourage you to put in different numbers and play with this script just to get an idea of what's going on, because understanding this simple model will be the key to understanding the Black-Scholes equation.